point for everyone here. Do more in person.
Well, the problem is, like I said, this has to be offered asynchronously. So back in the day, when it was only live in person, I still would report classes. Then it would have been okay to do it. But
Oh, so there's students that are like completely online.
yeah, there are people that live in Portland or the
Oh,
Portland area.
wow.
Yeah, that do everything remotely. So that's how we make it work. Okay, let's get started. So this is up on Brightspace. This is a more detailed discussion, kind of consistent with what I've done in my other class. And I do this because the content here is a lot more, I don't want to say challenging per se, but there's more concepts and whatnot that you haven't seen. So there's a little bit more narrative discussion about how to do some of these things. So we'll go through the review, and then I have a problem that we'll do with Laplace, and we can do sort of the whole, full Monty approach to doing it. But like I said, this is available to you in the content folder for today's class. I think it's class 24, I believe. All right, so the first concept is something we actually focused on with the last exam, but it is so important to be able to do this material. And it really is the key for this semester, in my opinion, is to be able to use Laplace to solve any differential equation, right? Any homogeneous time invariant differential equation. So I put up the discussion, but the key thing is we're not going to do derivations on this one, right? This exam. We're just going to have to be able to go back to the time domain using inverse or partial fraction expansion to go back into the time domain. So I reiterated the three approaches that I taught you in class. I had a student that stopped by yesterday that talked about using the AS plus B approach. Like if you have complex roots, and you can't factor them out, I don't know. Let's say that's complex. And then you have over here, you have AS plus B over that. And then you can break that up into AS over S squared plus 3S plus 7 plus B over S squared plus 3S plus 7. This works perfectly fine. But again, it's a modification to the approach that what we do. It's more succinct, in my opinion, to go ahead and immediately calculate a complex number that has a magnitude and an angle because your output only has a sign. If you remember, this here translates into the sine, and that is the cosine. So you have two time domain expressions that could be combined, right? You certainly could combine them using Euler's identity to go ahead and get a magnitude and an angle, or you can just go ahead and, very quickly go ahead and do that. And that's this case 2 that we described there. So all three cases use generally the same approach, but case 2 and case 3 need slight tweaks. So case 1, we have real non-repeated roots. Go ahead and do your factoring all the way out to get your denominators so that they can be to the base that they can go. And then we're going to go ahead and write all the coefficients, A plus B plus C, on and on and on. And then we solve for those coefficients, the A, the B, and the C, multiplying both sides by whatever term, whatever coefficient you're trying to solve for, and evaluate at the root of that denominator term. That's case A, or case 1. Case B is if you have complex roots, now we can go ahead and do the same approach on case 1, but then we would end up with e to the j thetas in our time domain solution, which is what we don't want. So we solve for a complex number b at an angle of theta when we have two complex conjugate roots, okay? That means it's a real part plus or minus an imaginary part. And so when we do that, again, we multiply by whatever is under the complex number that we're trying to solve for, and then we evaluate at the positive complex root. So that would be the real part plus the imaginary part. And then you solve for A or B at an angle of theta. The last case, again, is just similar, but if you have real and repeated roots, you have to go ahead and solve for the highest order root that you have, and then to solve for the next coefficient, the next root coefficient, you're just going to take the derivative of both sides. Everything else is exactly the same. multiply by whatever the highest order root is, take the derivative, and then evaluate at the root. And then you should be able to solve for that coefficient you're trying to get. All right. So super important to do it. We need a lot of practice. That's why we keep continuing to discuss it. Next semester, if you take the follow-on class to this, we'll actually spend more time living in the Laplace domain, trying not to go back to the time domain, because partial fraction expansion can be cumbersome and take a lot of time to do it. All right, so that's sort of revisiting, if you will, Laplace, but very, very quickly, very high level, but more importantly, being able to go from the Laplace domain to the time domain. All the other stuff, right? Multiplication by S in the Laplace domain is the same thing as taking the derivative. Dividing by S in the Laplace domain is the same thing as taking the integral, et cetera, et cetera. So all those mathematical properties that we used or developed for Laplace still applies for this exam. And it has to be because we're doing Laplace domain circuit analysis. Instead of doing L di dt or C dv dt, we can go S times L, right? Or C times S times C, right? We can get those same things. So we're taking advantage of the mathematical properties to do circuit analysis. So what we need to do is convert our time domain devices, right? Capacitors and inductors. And then we add in any, if we have it, we add in any initial conditions that we have. So for this inductor circuit, we have the inductor with a power source if there's an initial condition. Or we can have that same inductor converted again to the Laplace domain. And now we have a current source that's in parallel with it. Either one of those are the same, and you will notice that either of them is based on using my initial condition for current in an inductor, because the current can't change instantaneously in the inductor. So I can actually more rapidly calculate what that parameter is. I don't have to calculate another value like I would for voltage. So either one of these is perfectly fine. You just get to decide. If you're doing nodal analysis, it might be better to do the parallel equivalent. If you're doing mesh analysis, you might want to do the series equivalent. Again, it really just depends on whatever circuit analysis tool you want to use. Either one of them are perfectly valid. So that's our inductor. Here's our capacitor. So our capacitor, as you can see, same thing, right? We convert our capacitor to the Laplace domain by doing 1 over SC. Now we put our initial condition in there, and if it's a parallel circuit, we have a current source. And if it's a series circuit, we have a voltage source. In either case, the initial condition is dictated by the voltage, right? The voltage is what drives the initial condition. And the reason why that is because you can't have an instantaneous change in voltage in a capacitor. So again, it makes things much more efficient to do that. If you remember from AC circuit analysis, if I plug in S equals j omega, right, for an AC signal, because an AC signal just has a j omega term, there's no DC offset, then that becomes j omega L. Isn't that equal to the reactance term that you've been doing or have learned in AC circuits? Should be, right? Isn't that just J times X of L? Omega L is 2 pi FL, which is where we get our AC circuit. If you did the same thing for a capacitor, again, we stuff in J omega, we have 1 over J omega C, which is negative J times the reactance for a capacitor. Exactly the same as if you were taught in AC circuits. Do y'all remember that in 312, or if you took AC circuit analysis someplace else? Do you remember the reactance terms? No? You're saying, that means not sure. It's okay. You can say it's going over it now. You just started going over them now?
Well, we're going over some. No, we haven't yet started, but we're going over.
Okay. Because the whole thing about AC circuit analysis, and the reason why we can simplify it a lot, because if you had resistors, inductors, and capacitors, you'd have to write differential equations for AC circuits, right? It's the same thing, isn't it? But Laplace means we can write everything in as multiplication, but we have to do the Laplace domain. It's better to do things with AC circuits because we're looking at averages over one complete cycle. And so what that does is that it doesn't change over one cycle. It's a constant frequency. What ends up happening is our calculations are much, much, much easier. And so the whole thing about J and JXL or negative JXC, it all simplifies down from there. Do you know where you get the J omega? Whoops. Why didn't that flip over to here? That was weird. Right? That's the equation. Where does a J 2 pi FL come from? Well, let's go back and do L di dt, correct? So L di dt is the base equation for calculating the voltage drop in an inductor, right? So I of t, just sine of omega t, right? Just some magnitude, we'll call it 1, and has sine times omega t. That's an AC waveform, isn't it? Could be a sine wave, it could be a cosine wave, but that is a sine wave. So the derivative of I of t, what is the derivative of I of t equal to?
It's omega t cosine.
Omega, not t, but omega times the cosine of omega t, right?
Right. Chain rule.
Chain rule. Now I can plug that into here, right? Or let's check to see. So this is equal to L times omega cosine of omega t, correct? Well, we have our omega term here. That looks good. We have our L. We also have a J term in here. Where does the J term come from? Well, the problem is the sine wave is our reference. That does this, right? Our cosine wave does this, right? Isn't a cosine wave really just a sine wave that's been phase shifted by 90 degrees?
Yes, it is.
So this is equal to L omega sine of omega t plus 90 degrees, right? If I want to take the average of that, I know that the average of this sine wave is going to contribute 0. But now I've got this 90 degrees in here. So if I want to do things and multiply complex numbers together, 1 at an angle of 90 times L omega sine of omega t, these are now in phase with each other. 1 at an angle of 90 is just J, isn't it?
Mm-hmm.
So if I take the average value, my sine term goes away because I integrate over one period, and I end up with here. It all comes from writing your base equation, dl equals L di dt. Okay? You also could have done S times L times I of S, right? Isn't that the same thing? Taking the derivative is multiplying by S. You get the same result here. You have S times L. If I figure out whether that's a sine or a cosine, take the average value, the I term goes away, and I end up with S times L or J omega times L. So all this stuff comes from the math that you go ahead and do that. Does John not show you where the J omega L comes from or the J omega C negative J? What's that? or Rick, but did they do the derivation to show you where that comes from, or did they just wave their hands? Because at Eastern Maine, I'm a little surprised because their circuit analysis is not calculus based. So how can they show you where the J omega comes from if you don't show how to do derivatives? I'm wondering how he does that, is what I'm saying. LA? Okay. Okay, but that's just the derivation. And if you can do a little bit of the math, right, it just kind of shakes out. It's really a pretty simple, I think it's a pretty simple thing to see. All right. But the reason why we talked about that is, again, it all comes from the math. It all comes from the calculus. And with Laplace, we don't need to do that. So if you were taking like ECE or calculus-based circuit analysis, they would do everything in differential equations, but pretty quickly move to Laplace. Is that right, Arthur?
That's true.
Yeah. That's why they take circuit analysis as sophomores or second year students. Because if you've had Calc 1 and Calc 2 in your first year, then you're ready to do Laplace, right? So that's why most ECE majors take calculus-based circuit analysis as sophomores. If you take the calculus stuff out of it, and again, the only problem I don't like about taking the calculus out is you have to wave your hands and show where this comes from. You know, don't really just say, here's the result, have a nice day. It can get a little bit confusing. But if you can use the calculus-based stuff, it all kind of hangs on from physics. All right, any questions on Laplace domain circuit analysis? Because we just do everything in the Laplace domain. And if we do everything in the Laplace domain, Thevenin, Norton, voltage divider, current divider, superposition, KCL, KVL, max power transfer, all those formulas or those approaches that we developed for the time domain are still valid in the Laplace domain. There is no change. As long as you set it up correctly, any circuit analysis tool that you use in the time domain is applicable in the Laplace domain. All right. So that's why we spent the whole beginning of the semester. What did we do? All those circuit analysis tools, right? KVL, KCL, superposition, blah, 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 because we want to make sure that we have that strong fundamental understanding of how to do those circuit analysis, because now we're just doing circuit analysis in the Laplace domain. It's still circuit analysis, but if we introduce Laplace and it's confusing to do Laplace and it's confusing to do some of the circuit analysis, it really can trip you up, right, with the understanding. So that's why we spend so much time at the beginning of the semester reviewing circuit analysis. Okay. And then once we did Laplace domain circuit analysis, now we can just do things generically. And so generically means let's just use transfer functions. I don't care what the input waveform is. I couldn't care less. I just know that once I know what the input waveform is, I can calculate what the output waveform is going to be based on multiplying the input by the transfer function. And so Laplace is the only way you can do transfer functions, because you're multiplying the input by the transfer function to get the output. You can't do that in the time domain because you got to do integrals and derivatives, right? So you're not multiplying, you're taking integrals and derivatives. But in the Laplace domain, you're just multiplying, so you can do transfer functions. You still do transfer functions in the time domain, but all your circuits have to be DC. Remember we did our op-amps discussion, where we did inverting op-amps, and we looked at integrators and differentiators. Well, we can figure out what the gain of the system is if those are not integrators or differentiators, and then you had negative RF over RI. That's a transfer function for that op-amp circuit. I don't care what's inside the box. I just know that if I take an input and I multiply it by this transfer function, I'll get the output. It doesn't matter if I'm using op-amp circuits or if I'm just writing equations on paper. I should get the same results. So we'll take advantage of transfer functions because what we're looking for is how the system is going to respond to different stimulus. And it's way more important as we start to do more design, because what if the stimulus is 10 volts DC? All right, the system looks okay. What if it's 1,000 volts DC? What if it's a sinusoidal input? We don't know necessarily what those signals are going to be coming into it. So we actually have to have an ability to examine the performance characteristics of our system. And how do we examine it? We just look at the transfer function. Okay. When we do a transfer function, we have to assume all initial conditions are 0. And it's okay to do that because for the most part, our output is not really going to depend all that much on those initial conditions, especially if you look at things over a longer period of time. So generally speaking, we will ignore any initial conditions. And then when we have the transfer function, again, we're looking at system performance. So one way to really tell very quickly how this system is going to perform is to look at the locations of the poles and zeros and where they reside on a pole zero map. So poles are the roots of the denominator. Zeros are the roots of the numerator, except if you have more poles than zeros, those are finite poles, you actually have additional zeros as your S gets to be a bigger number. So what this says is the number of poles always equals the number of zeros when you allow S to approach infinity. And that won't make a ton of sense this semester. It'll be a lot more useful next semester when we start looking at things called root locus, when we have to terminate our what we call root loci. We need to terminate them at zeros, and so we'll start to see where that makes a lot more sense to us. But again, looking at a pole zero map, so this is the real part, and this is the imaginary part. Poles further away from the real axis are going to translate into different performance characteristics. So this is a pole, we'll call it A1. That looks like e to the minus t times A1 when we take it back to the time domain, or e to the minus t over 1 over A1, right? That's if we write it as a time constant. So tau is equal to 1 over A1. So the smaller the number of A1, the bigger the value of tau, right? 1 over 0.1 is going to be a lot bigger than 1 over 10, right? And since it takes around 5 time constants to reach steady state, or for this decaying exponential to finally be decayed, then the further we are over here, the faster the system reaches steady state. Okay? So again, talking about performance characteristics, if I look at my pole zero map, if I'm really close to the j omega axis, it's going to take a long time for that system to be stable. But if I'm way out over here, it's not going to take a long time at all. It's going to reach steady state much, much faster. Okay? So again, we do pole zero maps to assess performance. We also can look at poles that are not on the x-axis. We know that this is plus and minus j omega, right? Omega is the frequency. So the closer these are to the real axis, the less oscillatory it's going to look, right? The frequency is lower. But if we're way out over here someplace, then it's going to oscillate a lot. It still will decay away, but you're going to see a lot of oscillations depending on how, what your decaying exponential looks like. Okay? So again, telling us the performance characteristics. And once we have this information, and again, we're going to be looking at more complicated things next semester, we can actually determine how long things take to dampen out, or what is the overshoot going to look like. And so we'll start looking at these term damping coefficients and undamped versus damped natural frequencies. We'll start discussing those, and it's all based on the pole zero maps. One question people might ask, Paul, you only showed poles, right? I only showed X's. Why don't I show the zeros? Well, the zeros don't determine the performance of the system, right? They might have a little bit of an impact on the amplitude, but they really don't affect how long things take or what's the oscillatory frequency. But the reason why we include zeros here on the map is, as again, we're looking at more design, we have some parameters that can vary. Now we start looking at, all right, what if we start moving from a pole towards a zero, what does the performance characteristic look like? So we include those zeros in here to say, this is where this is trending, this is going in this direction, and so that's why we include those. So we want to make sure we have both the poles and the zeros identified on our pole zero map. Again, it's more of a looking for the future and being able to understand where these parameters, where these terms come from. Okay? Yes, sir.
What kind of, I feel like
Draw a pole zero map?
yeah.
That's the question. Draw a pole zero map. Or given a pole zero map, tell me what the transfer function should be. Right? At least the base transfer function. You may not know what the coefficients are, like if there's a multiple of 50, you know, like a 50 that multiplies the whole transfer function, but you could at least draw the base transfer function, or give me the base transfer function. Okay? Any questions on pole zero maps? Again, a lot of the stuff that we're doing this semester is just building that fundamental base so that next semester we can actually start to design more and more systems. And this stuff, it gets to be more and more important depending on the type of industry you go on. So we already talked about transients and switching transients in industry for the utility industry. But one of the biggest areas where this is super duper important is process control. So if you work at a paper mill and you're trying to control the level of a tank or trying to control the flow rate, having a good control systems base will massively help you understand how to tune these things. I told you one of my jobs, I spent about 6 months working on a project in Salem, New Jersey. Actually, it's in Salem, Delaware. This is useless information, but if you look at a map of New Jersey, what's that? Well, then you'll love this, right? Let's go to here and let's type in New Jersey. So there's an image of New Jersey, right? And you look at that and you say, wow, New Jersey is, this zoomed in area, right? And you can see the little dashed lines all the way around. See the little borders here? Except, look at the tip of New Jersey. Let's see, where are we here? So this actual is not correct. New Jersey actually, if I could draw a line, that's the end of New Jersey. So this little part over here, that's actually in Delaware. This is actually called, it's actually called Artificial Island. It was built to house 3 nuclear power plants that are there. And I'm really surprised Google Maps screwed this up because it looks kind of weird, right? To go this jiggy jag around here, unless maybe there was some decree that said, oh yeah, let's go ahead and let's move it, in the past 20 years that may have happened. But you can see it's really odd, right? This jag out where everything else is just following along the coastline of New Jersey, except for over here. I'm 99% sure that this artificial island, let's see if I can find that.
With that, what New Jersey regulations with nuclear power?
I don't know. I mean, this was built, Salem was starting to be built in the 60s, so. Let's see if it's actually in Delaware. Hey, but it has a small portion in Delaware, so you can see that even here, that this is actually, so it's mostly in New Jersey, but that tip, like I showed you, that actually is in Delaware. So anyway, I spent about 6 months. So over here, there are 2 units over here. And the owners of the plant at the time, which I think was Public Service Electric and Gas, had really screwed up bad. They had done mistake after mistake after mistake. So they ended up, the NRC took the keys away, saying you aren't competent to operate your plants, so you aren't allowed to run. There literally is no key to a nuclear power plant. You don't actually turn the key and to start it. It doesn't work like that. But they basically send a letter saying you are not authorized to start your reactor up. And so they were shut down for a year or two. And one of the things they did is they had these control systems for these moisture separated reheaters, which is, if you've taken MET433, you learn about power cycles and steam cycles. And this type of steam that you find in a nuclear power plant tends to be saturated steam. It tends to be lower quality steam. And so these moisture separated reheaters are unique. You usually don't have to separate with moisture in the steam. But in these, because they run at such a low temperature based on the pressure they're at, they actually have that need to do it. So anyway, one of the nuclear power plants, both of them, they use these old systems called Foxborough IA that had not been maintained. Again, the owner didn't do a good job of maintaining it. And so the system engineer for one of the nuclear plants said, we'll go ahead and test the system up, but most of the modules were broken. So what they ended up doing was scabbing a bunch of these modules from one unit and bringing it over to the other unit. And so my job was to replace this Foxborough IA control system with PLC. Basically, it was a Modicon Quantum. And the problem was, at the time, nobody knew anything how this control system worked. It was all, kind of black magic a little bit. So I spent 6 months doing a computer program on the PLC that actually took control and would bring the moisture separated reheater. So what it would do is it slowly would ramp up the temperature, but not too quickly, because you could actually damage things. So you had to bring it up slowly. And then if things were a problem, it would jump over from automatic mode to manual mode. Well, I actually got stuck there for 2 weeks during the startup. They wouldn't let me leave because it was critical. But the new NRC had given them the keys to the plant, saying you can go up to 50% power. Well, they went to 47%, and then the operators were yelling at me, you better not screw up this moisturizer separator reheater control, because the way that you actually make more power out of a nuclear power plant is you cool the steam down. So if I had cracked the valves open too quickly, they were concerned it was going to go above 50%, and they were going to get a big fine from the NRC. So I remember them threatening me, saying this better not go above 50%. And so I said, well, why not take it down to 40%? Well, we can't do that because we need the money. We need the money. We've been shut down for 2 years. It's like, so you're putting all this onus on my control system to work, and nobody even knows how it really works. So anyway, that was Easter weekend, actually. I remember spending Easter weekend in the bowels of a nuclear power plant with no light, making sure my moisture separator reheater system worked. And it did. It stayed in automatic mode, where my compatriot, who converted all those modules and scabbed them all over, when they started her up, hers actually wasn't able to stay in automatic mode. So the operators tripped it to manual mode. And then they ended up replacing it with my exact same system. So, but the reason why I'm telling you this is this was a control system. You actually had a proportional plus integrator control system, and the moisture separator reheater itself was a first order process to go ahead and heat up slowly. So that's the type of stuff, if you do process control, you can do it. You can spend 6 months down in Salem, Delaware, not Salem, New Jersey. So anyway, but yeah, you can say this is a pretty big, there's 3 nuclear reactors. There were supposed to be 4 at one point. You can see this kind of space over here. This is Hope Creek. It's a much newer plant. I mean, much newer. It's probably like from the late 70s, early 80s. But these 2 were built in the 60s. But a lot of power going on. And those plants still run. They make a lot of money for whoever owns them now.
So these folks
All
that were
farmland.
like
It's all
threatening,
farmland.
yeah,
This is
these
South
folks,
Jersey. So even though I'm not a gambler, so it didn't matter, but Atlantic City was only like half a mile away. So Atlantic City, you can see, is like right here, and this is artificial. So it's maybe half an hour to get to Atlantic City. I never went. I was also working really long days, but yeah, never went to the Jersey Shore, even though I was half a mile away.
Is that the big bridge?
Chesapeake Bay Bridge is
Oh, no.
that's way down yonder.
right here. See, it says Route 9. That's the bridge. That dumps you right into Well, that's not the Chesapeake Bay. That's Delaware Bay. The Chesapeake Bay
Yeah.
one's over here. It's
That's a
down-
that's a tunnel. I've actually been through that.
It's actually multiple tunnels.
Yeah.
There's two sections of tunnels. Yeah.
Yeah.
But yeah, that's kind of the lay of the land. So anyway, sorry I got sidetracked. And here are the test questions.
Okay.
I have an example if you want to work an example for circuit analysis,
Sure.
or we can answer whatever questions you may have.
Can we do an example?
You guys want to do it? No problem. All right, have fun. Can you do it? Give you 5 minutes?
Sure.
That's not a yes.
Yeah, we can do it.
If you want to try it. So nobody wants me to get you started then? That's fine.
No question.
Go ahead. Yep. They're both DC, right? Can anybody help Henry in what that means? 1 volt plus 1 volt UT? Uh-oh. You said you wanted 5 minutes to do the problem. How are you going to get started if you don't know what the power supply is? You want to make this your test? You get this problem right, get 100, you get a problem wrong, you get a 0. The whole world has shifted to gambling, right? Talking about Atlantic City. Anybody want to gamble?
No.
This is not real gambling though, right? This is just you all using your brain capacity. Luke.
Well, the E2 is unit stuff,
Mm-hmm.
so
For TV land, Luke asked the question, UT is the unit step, and I confirmed that.
Mhm.
Keep going.
could it just be two different power sources that are just in theory?
Sure, that's fine. So what does that mean? Two volts? 2 volts UT? I don't think so. Because otherwise I'd put 1V plus 1V parentheses and then multiply that by UT. I only have one of the 1 volt sources multiplied by UT. So how do you tackle this problem?
Oh, is it an initial value?
Yeah. So to solve this circuit, oops. That's 200 micro, sorry. 20. You got to solve your initial conditions. Right? So this is the T equals 0 minus condition. So I'm solving for T equals 0 minus. So our circuit analysis is based on using I's for inductors, right, for initial conditions, and V's for voltages. So you got to solve for your initial conditions. Think you can tackle that? I hope the answer is yes. You shouldn't even have to write this down. You should tell me, what does IL of 0 minus equal? Anybody?
So, going back to the source, so that 1 volt plus the 1 volt UT was this at 1 volt in steady state and then you added an additional volt?
That's at T equals 0 minus. I'm just looking for my initial conditions.
Okay.
So this here doesn't exist until T equals 0, right? So that
Okay,
second
so it's
1 volt does not exist
all
until
right. So it's off
so
at t equals 0.
off,
It's
right?
off. Yeah. So there's no current, 0.
IL of 0 minus is 0. Everybody agree with that?
Yeah.
Very good, Henry. It's 1 divided by 20 because the inductor shorted out. What about here? What is that? Yep. So what's the voltage VC of 0 minus equal to? 0? Everybody agree with that? Austin, I think you said it, but you said it so quietly. Say it louder and be proud. Yeah, it's 1 volt. Because all of that 1 volt source is being dropped across the 20 ohm resistor, which is the same potential as the capacitor. So I've got here and here. Now, oh, cancel that. Redraw the circuit in the Laplace domain with your initial conditions. Go ahead and give it a whirl. Does anybody want to see the circuits that you need to the Laplace domain equivalence? Would that be helpful? Yeah. See if I can make these small enough so you can see them both. Almost. Let me see if I can do 2-page view. No, of course not. How about that? So you have an inductor and a capacitor. So you got to use Laplace, right? Because it's not a first order circuit. So draw your circuits. And what I'm looking for is I want to know what VC of T equals. All right. Anybody got the circuit laid out? Not quite. Okay. Everybody still see my screen?
Yep.
Okay, thank you.
Paul, what are we solving for again?
VC of t.
BCFT. Okay.
Still need time to draw your circuits, or can I start laying them out? Okay. So at time t greater than 0, now this becomes 2, right? Because it's after 0, but it's not 2. It's 2 over s, right? Because we're in the Laplace domain. Now we're going to go to our inductor. The question is, should I do parallel equivalent or the series equivalent? You can do the series, but I'm looking for the voltage here to here. Wouldn't it be really good if I just did nodal analysis to get the voltage there? And with nodal analysis, it's usually easier to do things with currents and not adding additional nodes. If I put a series circuit, then what I have introduced is another node. So I'm going to do the parallel equivalent. So I've got S times L, and I've got to have a current source here, and that current source has to be in the direction of the initial condition, right? I can't put the arrow going in the opposite direction because it wouldn't hold, right? I can't have my initial current going one direction, but this says the other one. So that's going to be equal to my I0 over S. This is equal to I0. Now I drop my resistor, no big deal. That's R. What should I use for the capacitor? Do I use the series or the parallel equivalent? Keeping in mind, I'm planning on doing nodal analysis.
Use the series.
Well, I might argue you want to use the parallel because I'm introducing another node when I do the series circuit. You certainly can, but I would rather do the parallel equivalent. I think.
Okay.
That's 1 over SC. And then I have C times V0. Now, somebody who might be asking, hey, Paul, why did you put the arrow going up instead of down? How do you know the direction? Because if you look over here, I've got a plus to minus voltage in that direction. And my initial condition said this was plus to minus in that direction of 1 volt. So if I want the positive to negative to be consistent with the two, I'm going to go ahead and draw it that way. And this is VC of S. You want 5 minutes to go ahead and do this one?
Sure.
Okay, go ahead.
If we did happen to do this new circuit, if VC of S over the voltage source and the capacitor, is it both of them, or is it just the capacitor?
Excellent question, Henry. So just give me 1 second. I'll zoom in. So Henry asked the question saying, if they use the series equivalent for the capacitor, is that correct? Should it be the voltage V odd over S? Or should it be 1 over SC? Or should it be the combination? And the answer is the combination because of the plus minus V. That is the total voltage across the capacitor. So it has to be the sum of those two. Okay, very good question. That's why if you look, adding the blue, showing the VC or the V and the I, those are the important parts. Even when look at the parallel equivalent, right? If you look at the parallel equivalent, you can see the voltages across those two elements, but look where the current goes. It's not on the initial condition, it's the total current going through the capacitor. Okay. All right, 5 minutes. Unless you want less time. Oh, it's starting to flurry. For those of you who are not in Orno,
It is here too.
yeah, there's just a little bit of flurries on the ground.
Yeah. It's just starting to sprinkle down. And I'm 70 miles south of you, so
I've got new tires on my car, so I feel, even though I'm in my Prius, still feel pretty comfortable.
I need new shoes for my cruise, but
New
I've
brake
got
pads, you mean, or brake shoes?
no tires. I call them
Oh.
shoes.
See, I'm really old because they used to be, there would be pads and brake shoes when you would drum, the old drum brakes.
Yeah.
You say shoes, I think of the brake shoes.
The yellow bug has 4-wheel drum brakes.
Oh, wow.
Yeah. And they're
Very
not
good.
self-adjusting.
And there's no power assist either, right?
No, it isn't. It's whatever you can mash through that pedal with your foot.
You better have strong legs. Although the
doesn't
car only
take
weighs like
much.
1,800 pounds, so,
Yeah, it doesn't take much.
right.
You'll lock them up if you're too aggressive.
No ABS on that thing.
Yep.
Oh. Night and day, even in the rain, like my tires had enough miles that are not great. So I replaced them like at $700. Well, that's cheap though for my little Prius. It's 15-inch tires.
Yeah.
So none of you guys have 15-inch tires. Maybe Arthur maybe Arthur actually has 13-inch tires.
What?
You got 13-inch tires on your Beetle?
No, those are 15s.
Wow. Sports car.
Yeah, but the rims are 4.5 inches wide, so
Wow.
they're like little
My
pixie
very
cups.
first car had 13-inch tires. I don't even think you can buy 13-inch tires anymore.
No, my old Buick I had 14-inch wheels.
Yeah. Now you're rocking 20s. I remember when rap stars used to brag about rocking
Yeah.
sneakers that were 20, and it's like nowadays you can go, you can buy a Toyota Venza with 20-inch tires. It's not that impressive.
Yeah, no, my Chevy Cruze has 18-inch tires, 18-inch wheels on it.
Yeah, and that's not a performance car.
No, but the appearance package got you from 17 to 18-inch wheels.
Fancy. You want the appearance package.
Yeah. Well, I got them both used. That's what they came with.
I'm kidding. You know, I just did a class yesterday on financial awareness for college students, and we talked about being smart.
Yeah.
Everybody wanted to buy a $60,000 Audi Quattro, blah, 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 with all these.
No.
I had them buy a Toyota Corolla and they.
Yeah. I was gonna say you can always bet. I mean, as sure as the sun will rise tomorrow morning, a Corolla will still be around for 20 years if you
Amen.
take care of it.
Amen to that is right.
But more importantly, I saved them, I showed them how that one difference cost them $300,000.
Anything.
Yeah.
I don't know.
Yeah, you're better off just buying something good and taking care of it.
Mm-hmm. You won't impress a lot of people, but that's okay. Impress
No.
them with your amazing charm and wit.
Yeah, I was gonna say what somebody drive doesn't impress me. I've seen it all.
Well, Arthur, we're not in the generation that would be impressed by fancy cars, so we aren't the best people to ask.
No.
Like you're running off of the business. It's like flash your fuel economy numbers.
With 154,000 miles
Yeah.
from 2012,
Yeah.
you think I'm flashing?
That's what everybody's into now.
Wow.
You can get 40 miles an hour.
Depends. So if I had to go back and forth to Boston, I drove pretty aggressively and the temperature really affects it.
Yeah.
So I was like 39, 38. If I'm driving at a, reasonable highway speed, I can get 45 or 47. If I'm just driving in town, I can get 53, 54.
Those are the best in town. Like,
Yeah.
Half the time it's just electric.
Even if I'm not using electric, like, cause I can plug mine in. If I don't use electric, I can still get 50, something like that. If I'm plugged in, I can get infinite, I can go about 12 miles on a charge, but that's kind of cheating. It's not free energy, so. All right, what do people have for answer? Anybody?
Hmm.
Well, I hope you get started. Here's VC of S, right? So let's do some currents in here. I have current this way, this way, this way, and that one's already taken into account. So I have VC minus 2 over S divided by SL. That takes care of that current. That's current into the node. Plus, this is a current, right? That's amps, so there's that one. Now, plus C times V0. Those are all the currents in, right? I get check, check. That's going to equal the currents out. VC over R plus VC over 1 over SC. So let's do a little bit of factoring. Let's see, VC times 1 over SL. Minus 1 over R minus SC plus, let's see, that's negative 2, whoops, negative 2 over S squared times L plus I over S plus CV naught equals 0. VC times RC times S. So this is R minus SC minus S squared C R plus, or that equals positive 2 over S squared times L minus I over S minus C times V naught. So VC is going to be equal to RCS over negative minus SC plus R, all of that times that's your final answer. Now you'd have to do partial fraction expansion. Keep in mind, this is a number, right? That's a constant. There's no S terms in here. You've got an S squared term here and an S, so you've got some partial fraction expansion to do. But in reality, you've only got, 2 roots here. You've got 2 roots here, right? Because you can factor out the C, so that's S equals 0, 2 roots there that are repeating. and one that is at S equal 0 or DC. So you do partial fraction expansion at this point.
Can you go back up to that first equation, really?
Right here?
Yes, and then just hold it up for the circuit too. So you have the current, the inductor that you split into the parallel, or equivalent up on the top.
Yep. I think what you're saying, should this be backwards?
Yeah.
Yes, that should be 2 minus S, 2 over S minus, yes, so that should be backwards. So this is going to be, let's see, that's positive. This is negative. And this is an L, so I have SL, and then this is SCL here. I think that's the only change I need to make. This is plus. Let's see, do I have that correct? Yes, I believe I do. So yeah, you just have to swap the polarity around. Let me just redo it. Can I just redo it all? That way there's no confusion.
Yeah.
So that way there's no guessing as to which way the polarities are. All right, so we're starting over here. That's the only sign chain I made is here. So let's do it again. So this is VC of S times 1 over SL. That's the first one. Minus 1 over R minus S times C, right? Plus I over S plus C V out. And then I have to have that one over there. So that becomes plus 2 over S squared times L. And that's going to equal 0. So VC of S times, now let me put this under a common denominator, right? SL times R. So I've got R here minus SL minus S squared CLR. Those are all those putting under a common denominator. That's going to equal negative I out over S minus CV naught minus 2 over S squared times L. So VC of S is going to be equal to SL times R, negative S squared CLR minus S times L plus R, all multiply by that. So at this point, you do partial fraction expansion. That's when you do the 3 cases, case 1, case 2, case 3. You actually have all 3 cases here because, or possibly, because this right here might be complex, repeating root, and a real root there. Okay? It actually would probably make sense to do this one. Well, yeah, you probably would just multiply it out and then just break them up individually. So what I mean by that is it would be easier just to do this. This is LR over here. Right, that's multiplying the first 2 terms. And then the next one is minus C V naught SLR, oops, over negative S squared CLR minus SL plus R. And then the last one is minus 2R all over S times negative S squared CLR minus SL So like this one right here is already down to partial fraction expansion, so that's no work there. So this is a sine, that's going to be a cosine, and this one you have to do partial fraction expansion. That's why I didn't combine these and put them under a common denominator, because I would have had to do more partial fraction expansion. So I just broke them out separately that way. So it looks like a lot of work, but it really is just keeping track of the math, right? And again, if you don't like to do the parallel combinations because you find that these are too complicated, then just go ahead and do the series one. Figure out whichever one you want to do. Either one will work and get you the same answer. It's just maybe this one is more work than you want to do. And you can go ahead and do that. Questions on this? Because one of your classmates had a specific question, like, can we do a problem? If you can do this problem, that's pretty much the whole Monty, right? We actually had to go back from previous chapters and figure out initial conditions. So we went through and showed how, and hopefully one thing I did, I skipped a step a little bit. If this step here was too complicated, the t equals 0 minus, then my suggestion would be redraw the circuit with your components in steady state, right? So that is a short circuit now. Because a few of you had a hard time seeing where I got the IL equal to 1/20 or the VC equal to 1, right?
Mm-hmm.
So if you're stuck doing that, if you're stuck with that, just go back to, all right, we've achieved steady state for the inductor and the capacitor, which means I've got a short circuit for the inductor because it's no longer generating an opposing voltage, and the capacitor is as charged as it can be, so there's no current going into the capacitor. That's represented by an open circuit. Remember that was what, a month and a half ago, 2 months ago? So see how this stuff builds? This is why this problem is, there's a lot to it, right? But in reality, the t equals 0 minus circuit is something hopefully you all are pretty comfortable doing, especially if you draw that circuit there. That one kind of screams at you what the initial conditions are. And then the next one is, all right, let's go ahead and build that circuit. And because there are a lot of components, right? Because we include those initial conditions, that's why our nodal analysis had so much to it. But once we simplified it down, we don't get a crazy amount. And if you don't like negatives here, no problem. Make that a plus, make that a plus, make that a plus, and then this becomes minus, doesn't it? Just multiply the numerator and the denominator by -1. And then minus. Same thing over here. Plus, 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 minus. But I know those negative signs can look a little intimidating. Just cross them out, cancel them out. They don't really change all that much when we cancel them out that way. And I think. Good example, not a good example. Tied in a lot of concepts, right? We didn't do partial fraction expansion because that's just, I'm not going to be so interested in doing a circuit this complicated and say, give me VC of t. That'd be a lot of work. And a lot of, unless you want a problem like that. You want me to write a problem like that?
No,
Arthur, I would have thought for sure you would have said yes.
no.
You love doing the math. But you see the idea, what I'm looking for is I'm looking less about being able to go back into the time domain because that's not the focus of this test, but it's still a really good thing. That's why we're uncovering it. And you might have to be able to go back into the time domain, but not quite as much algebra as this. Okay. Again, unless you want to do a lot of algebra. But I don't see a lot of value in forcing you to do a problem like this. Questions for me?
That's like. Class that you find online, a lot of football examples, and, you know, it's much more difficult, I think, to you find, like, there's the football stuff, you have like a good resource where I can like get answers, I can make up my own problems, I don't know if I can, but,
I searched this one this morning. I just did Laplace domain circuit analysis. And that example that we just did, right here. So if you type in the right keywords, Laplace domain circuit analysis, the example we did is right here. I did it differently, right? Because I actually showed you how I would do it. But it actually goes and does the full Monty all the way down with a plot. Here's another one. No, this is
yeah, we're an acrobat.
all I did was, I'll tell you what I searched. Whoops. Laplace circuit analysis examples. That's what I typed in. That was the very first problem thing I found. It's good real time, right? You're like, how did you find all these things? They're like, this is what I did. You can also use the Shom's this outline series. That may or may not do it with Laplace. I'm not sure, but it should have someone with differential equations. And I suspect there probably is Laplace in there because most of the time when you do circuit analysis, you don't do a lot of differential equation solution because that's just a lot of math. So I would imagine the Shom's outline series for electric circuits probably has a ton of good examples. But like I said here, and again, I'm trying not to be mean or trick you or anything like that, but literally I just clicked on that and I said, okay, this looks like a similar concepts if it now won't load up. So I don't know, has the internet been slow for people this morning? Because mine, it seems like it's been hard. But you can see these are the problems, the first problem we did. And I just said, yeah, this is a perfect example of what I'm looking for. So let's just do that. If you can grind through those examples backwards forwards, test should be pretty simple. Other questions in TV land or elsewhere? I did start class a few minutes early, but it says we've got 4 minutes. Do people get frustrated when they look at the video that I posted and it says it's an hour and 18 minutes? The class wasn't supposed to be an hour and 15, but do you get annoyed when it's more than an hour and 15? Some people tell me.
When I'm looking at the recording, so I'm not watching the whole thing through.
Okay.
I'm like finding a spot where I know you want to look at something that I want to revisit.
Okay.
But I'm never usually watching it like starting to end.
Well, somebody said that 2 weeks ago. They said they get frustrated when the class is more than an hour and 15 minutes. I'm like, but you get something for free.
Right.
Is that really a problem? They didn't look at it that way. So
Interesting.
Yeah.
Really,
yeah, it's fine. It is what it is. I try to give you more than what you asked for, right? More than what you paid for. So anything else? Everybody know the deal? Test is on Friday during lab. It's right in this room if you can do it. I've only had a couple, I think 2 or 3 people say they're going to take the test online, so that's fine. But just make sure you check with me. I had a student actually, without getting a lot of details, they needed to do a makeup test sort of, or makeup time. And then I told them to check with the person to proctor, and they never did. And then they showed up at my office this morning saying that person is not available to proctor. Now it becomes my problem to fix it. So if you can't take it during the normally scheduled time, that's when we need more than 24 hours notice, because it's a 3-hour block and I have to work with the SCT office to make that happen. Because I can't, I got too many things going on a day with meetings and stuff. I can't commit to doing that amount of time. If it's during a lab, I'm locked and loaded. I block out my 3-hour window so that's precious. I'm there. Like I had an exam yesterday, right? and I blocked out that time. So I can commit to that. But outside of that, 3 hours it's a tough sell.
And we're doing the material on Thursday.
Yeah, we'll start to do a little bit more stuff with LaPlaz. Maybe we'll go over some of the stuff with LaPlaz, because I would imagine seeing that right before Thanksgiving was a little complicated. So we'll go through it a little bit more. I got other waveforms we can look at too. So yeah, I'll be doing that. But then if you have one or two quickie questions, just kind of studying up, because I would imagine nobody's really started studying for the test. It's fine, and I understand break, but you haven't started studying for the test, so you get the next day or two to get through, and then say, okay, I didn't get this, Paul. Can you explain that? But even then, if you get stuck, hey, with Zoom, office hours, just send me an email. We can go ahead and set up a time to work through stuff. I'm generally pretty flexible. Okay, any other questions? People in TV land must be feeling really bad because there wasn't a lot of correspondence and conversation, so that's a bad thing. But you got a couple days to feel better about. But with that all, have a wonderful day. Enjoy the snow and be safe. And I will talk to you. If I don't talk to you the next little bit, I'll talk to you on Thursday. Take care, everyone.
All right, thank you.
Thank you,
Thank
Paul.
you.
Thanks, Paul.
Thank you.